What time is it where you are? Is it already quiet outside? Have the lights gone down? And the world slowed just enough for your thoughts to stretch out? If you're here because sleep hasn't arrived yet, you're not alone. This is Sleepless Night, a calm corner of the world for the sleepless you and the sleepless me, a place where we follow gentle thoughts, just far enough to forget the time. Tonight, we're going to sit with the stars, the ones that shimmer, that flicker, that don't stay still. Why do stars twinkle? Not a mystery, not a riddle, just something to float with, from the surface of what we see to the deeper spaces behind it. We'll start with the simplest way to see it, and slowly, softly, move toward what even scientists are still figuring out. From level 1 to level 70. And you don't have to finish it all tonight. Just listen as long as your mind is curious, or until sleep finds you. If you enjoy the drift, tap like. If you feel like sharing, leave a comment with the time where you are and how you're feeling tonight. Include a timestamp if a certain part sticks with you, and if this feels like something you'd return to. Subscribe to Sleepless Night. I'll be here, just like the stars, quiet, steady, and waiting. Now, let's begin. Stars twinkle because the sky is wobbly. You go outside. The sky is dark, and the stars don't shine like flashlights. They blink. They shimmer. Sometimes they even look like they're dancing. But that's not because the stars are moving or flickering on and off. It's because the air above you is moving. Earth's atmosphere is like a giant ocean of invisible waves. Hot air rises, cool air sinks. Winds shift, pockets of turbulence swirl above your head. As starlight passes through all these layers of air, its path bends, just a little. Not once, but again and again and again. This bending is called refraction. Think of it like looking at a coin through the bottom of a swimming pool. The coin doesn't move, but the water makes it look like it's dancing. Shimmering. Changing shape. That's what the atmosphere does to stars. If you were floating in space, with no atmosphere around you, the stars would stop twinkling. They'd become steady, silent, perfect points of light. So twinkling isn't something the star is doing. It's something the air is doing to the light, on its way to your eyes. Simple, but beautiful. A flicker caused by the sky itself. The atmosphere isn't still. When you look up at the sky, it feels still, quiet, unchanging. But above your head, miles and miles of air are constantly in motion. Air isn't solid. It's fluid, always shifting. Even on the calmest night, there are waves of heat, ripples of cold, tiny storms we don't feel but stars do. As starlight travels through this ocean of motion, it bends, not in a straight line, but through swirls, layers, and little distortions. Sometimes the light reaches your eyes, straight and clean. Other times, it wiggles just slightly. A tiny deviation you can see as a shimmer. So when a star twinkles, you're seeing the atmosphere breathe. Invisible motion, revealed by distant light. Stars don't blink. The sky does. And your eyes catch it. In a moment of flicker. Bending light. Light travels in straight lines. Until it doesn't. When light moves from one material into another, from the vacuum of space into Earth's atmosphere, it slows down. And it bends. This bending is called refraction. You've seen it before. A straw in a glass of water looks like it's broken. A swimming pool looks shallower than it really is. Your hand in a bathtub might look like it belongs to someone else. That's refraction at work. The bending of light. As it moves through different substances. When starlight reaches Earth, it has to pass through layers of atmosphere. Some warmer, some cooler. Some thick with humidity. Others crisp and dry. Each layer bends the light just a little differently. And since the air is always moving, so is the bending. The star's light wiggles as it reaches your eye and your brain. Blessing and curse turns that into a flicker, a twinkle. Stars twinkle more than planets. You've seen it before. Stars shimmer like glitter in water. But planets, like Venus, Jupiter, or Mars, they mostly shine steady. Why? It's not because they're closer, though they are. It's about size. Not their real size, but how big they appear from where you are. A star is a tiny point of light, so far away that even through a telescope, it looks like a dot, a single beam of light, cutting through the atmosphere. Easy to bend, easy to shake. A planet, on the other hand, appears bigger in the sky. Not a single dot, but a small circle of light, spread out just enough. So when the atmosphere bends the light, the planet's glow stays steadier. It's like comparing a pinpoint to a glowing coin. One flickers, the other holds still. So now you know. Twinkling tells you. You're looking at a star, a sun, burning far beyond your reach. The sky is full of turbulence. You can't see it. You can't hear it. But above your head, the air is never quiet. High above the ground, invisible rivers of air weave and twist. Warm air rising, cool air sinking, wind shearing sideways. This is turbulence. The chaotic dance of the atmosphere. It's like looking through water that never stops moving. And the stars? They shine through it all. As their light travels through this turbulence, it bends, warps, scatters. Sometimes just a little. Sometimes enough to make the star look like it's fluttering or winking at you. The faster or more chaotic the turbulence, the more the twinkle. And on very still nights, when the air calms, the stars soften, their flicker slows, and they almost begin to glow steady. Almost. Because the sky never truly sleeps. And neither do the stars. Stars near the horizon twinkle more. Next time you look at the night sky, notice something small. The stars near the horizon twinkle more than the ones high above. Why is that? It's not the stars themselves. It's the journey their light must take to reach you. A star high overhead sends its light almost straight down, through less air, through fewer disturbances. But a star near the horizon has to send its light sideways across the sky, cutting through more atmosphere, more turbulence, more bending. Imagine shining a flashlight through a thick fog. The more fog the light travels through, the more scattered and fuzzy it becomes. So too with starlight. That's why stars near the edges of the sky seem to shimmer, pulse, even change color more often. It's not that they're weaker. It's that twinkling stars can change color. Have you ever seen a star flicker? Not just in brightness, but in color? A blink of blue, a flicker of red, then gold, then white again. Like a sparkler in the dark. You're not imagining it. The colors are real. As starlight travels through Earth's atmosphere, it's not just brightness that bends. Colors bend too. Blue light bends more sharply. Red light, just a little less. And as turbulence tosses the light around, your eye catches the mix. Sometimes the red light makes it through. Sometimes the blue. Sometimes both. But just for a moment. This is called atmospheric dispersion. A gentle scattering of color, caused by moving layers of air. Stars closer to the horizon often show this best, because their light takes a longer, more twisted road. You catch the scattered rainbow as it breaks and dances, before settling back into white. The star itself hasn't changed, but its light is playing with the sky, and you're lucky enough to see the result. Astronomers and the problem of twinkling. For most of us, twinkling stars are magical, comforting, almost poetic. But for astronomers, they're a bit of a nuisance. Telescopes, especially the powerful ones, need clarity, steady light, perfect focus. But the atmosphere never holds still. Imagine trying to read a book at the bottom of a swimming pool, with the pages rippling from the water above. That's what it's like to study stars from the ground. The twinkle blurs the details. It makes stars seem to dance, to pulse, to distort. Astronomers call this effect seeing. Bad seeing means a shaky sky. Images blur. Light spreads. Information is lost. So they adapt. They build observatories on mountaintops, above much of the thick air. They choose dry places, with less turbulence. And more recently, they've started using something remarkable. Adaptive optics. A way to cancel out the twinkle in real time. But we'll save that for level 9. Canceling the twinkle. What if you could undo the shimmer? Unflicker the star? Hear it exactly as it is, without the sky's interference? That's what adaptive optics does. It starts with a trick. Astronomers shine a laser into the sky, not to measure a star, but to create one. The laser creates a fake star, a tiny glowing point, in the upper layers of the atmosphere. Then, they watch how that point twinkles, because any distortion that bends the fake star's light is the same distortion bending all the starlight nearby. Tiny mirrors inside the telescope. Flexible, adjustable. Shift hundreds of times per second, counteracting the twinkle in real time. As the atmosphere wobbles, the mirrors wobble too, but in the opposite way. The result? A clearer, crisper view, like wiping fog off a window that looks out to forever. Adaptive optics let us see stars as they truly are, not as the sky makes them seem. And for a moment, The stars stop dancing. They breathe still, leaving Earth behind. For centuries, we looked up from Earth and dreamed of seeing more. But the sky, the very thing that shelters us, also blurs what we see. So in 1990, we did something extraordinary. We took a telescope and we launched it into space. Its name? Hubble. Unlike every telescope before, Hubble wouldn't have to peer through the atmosphere. No turbulence. No twinkle. Just silence. Vacuum. Clarity. And what it saw changed everything. It looked at a tiny, dark patch of sky. A space that seemed empty. And it stared for days. What returned was a deep field of galaxies. Thousands of them. Each one a whirlpool of stars. Some older than Earth itself. All hidden beneath our flickering view. Since then, we've sent more eyes into space. Spitzer, Chandra, James Webb. Each sees a different kind of light. Each undisturbed by the sky that once kept us blind. Up there, stars don't twinkle. They shine. Light is a wave. You may think of light as a line, a beam, an arrow, a straight shot through the dark. But light isn't just a line. It's a wave. Invisible ripples. Moving through space. Through time. Through everything. Light doesn't need air. Or water. Or anything to carry it. It rides its own energy. An electromagnetic wave. Oscillating gently. As it travels billions of kilometers. From a star to your eye. These waves have size. Some are short and sharp, like ultraviolet. Others are long and lazy, like infrared. But all of them, when passing through something, a lens, a drop of water, or our atmosphere, bend, just like waves in the ocean. Slow down near the shore. Light waves shift when they move from one medium to another. That's refraction. And different wavelengths bend differently. Remember that straw in a glass of water? Now you know why it looks bent. You're seeing waves being slowed, split, and scattered. The atmosphere, then, is not just air. It's a living lens that bends the cosmos. The color of twinkling. Not all starlight is the same. Some stars burn blue, hot, young, intense. Some glow red, older, cooler, heavier with time. And many lie somewhere in between. Their light soft and yellow, like the sun. But remember, light is a wave. And each color you see is a different wavelength. Blue light has shorter waves. Tighter, faster, more energetic. Red light stretches wider. Longer, slower, softer. And when these colors pass through the atmosphere, they don't bend equally. Shorter waves, blue, bend more, scattering and flickering easily. Longer waves, red, hold straighter, less disrupted. So a blue star might twinkle more sharply, more erratically, than a red one. And sometimes, a single star might seem to flicker through the rainbow, as the layers of atmosphere split its light and toss its colors separately toward you. A twinkle isn't just a shimmer. It's a spectrum in motion, a living fingerprint of light, color, air, and distance. And the deeper you look, the more you see how rich and restless the sky really is. Light takes time. When you look at a star, you're looking into the past, not because of a memory or a dream, but because of speed. The speed of light. Light moves fast, around 300,000 kilometers per second. That's fast enough to circle Earth 7 times in a single second. But the stars are far, really far. The light from the nearest star, other than the Sun, takes over 4 years to reach us. Some starlight takes hundreds of years, others thousands, some millions. So when you see a star tonight, you're seeing it as it was long ago. Some of those stars, they might not even exist anymore. They could be gone, burned out, collapsed, reborn. But their light is still traveling, still making its way to you, one tiny wave at a time. And when it finally arrives, it dances through our atmosphere, through your eyes, through your mind, twinkling with time. Light doesn't just travel, it stretches. When starlight travels across the universe, it doesn't stay the same. Space itself is expanding. Gently, quietly. Like the surface of a balloon inflating. And as space stretches, so does the light inside it. Its waves grow longer. Its color shifts. Blue becomes red. This is called redshift, a cosmic stretching of light as it journeys through expanding space. For nearby stars, the effect is tiny. But for galaxies far, far away, their light is stretched so much that it moves into infrared or even microwave wavelengths. We can't see it with our eyes, but with the right instruments, we can read it. Like a time capsule, redshift tells us how far that light has traveled and how fast the universe has changed along the way. So when a star twinkles, it's not just light dancing in the air. It's a messenger from a place stretched by time, from a space that never stops moving. And you? You caught it at just the right moment. Your eyes shape the sky. When starlight reaches Earth, it still has one more lens to pass through. Your eyes aren't perfect cameras. They're curved, organic, slightly flawed in ways that make each view unique. Your cornea, your lens, the fluid inside your eye, they bend light just like Earth's atmosphere does. A little ripple in the tear film, a tiny change in pressure, a moment of dryness, and the way you see a star can shimmer, double, or blur. Some people see halos. Some see spikes. Some see soft glow. The twinkle lives partially in the sky, and partially in us. Even the rods and cones in your retina respond differently. Your rods, tuned for darkness, can't see color, but they're sensitive to motion, to the subtle flicker. So at night, your eye leans into flicker and lets color fall away. You're not just watching the stars. You're shaping them as they arrive. The color of heat. Not all stars shine the same color, because not all stars are the same temperature. You've seen it before. An iron rod in fire turns red, then orange, then white hot. Stars do that too. Cooler stars, around 3000 degrees Celsius, glow a warm, deep red. Mid-temperature stars, like our Sun, around 6000 degrees Celsius, shine yellowish white. Hot stars, reaching over 30,000 degrees Celsius, burn a sharp, icy blue. The color of a star is its temperature revealed. But when that light passes through the atmosphere, those subtle hues get softened, scattered, twisted. Twinkling hides the truth a little. But the truth is still there. Astronomers use something called spectroscopy to break the light into its rainbow. And hidden in that rainbow are fingerprints of temperature, age, composition. So the next time you see a star flicker blue, or red, or white, know that you're not just seeing light. You're seeing heat. You're seeing physics. You're seeing time made visible. Level 17, gravity bends light. We're used to thinking that light travels in straight lines. But in the presence of something massive, a star, a planet, a black hole, light curves. Not because it wants to, but because space itself is curved. This is gravitational lensing. Einstein predicted it. If gravity pulls on mass, it should also pull on light. So when starlight passes near a massive object, its path warps. Just slightly. But enough to make the star appear where it isn't. The effect is usually too small to notice with your eyes. But telescopes? They see the magic. Sometimes we spot two images of the same star, split like a mirror. Sometimes we see rings of light. A perfect circle, called an Einstein ring. But even in small ways, gravity subtly shifts how stars look to us. And in rare moments, it can even magnify the twinkle. Like a cosmic magnifying glass. Focused by space itself. Gravity doesn't just pull planets. It bends the paths of star stories before they ever reach your eyes. Level 18, the sky isn't still. You may look up and think the stars are fixed, like dots on a ceiling. But they're not. Every star you see is moving. They orbit the center of the galaxy. Just like our Sun. They drift over centuries, across patterns we once thought permanent. This is called proper motion. A slow, steady dance across the canvas of the sky. And while it's too subtle to see on any single night, astronomers have measured stars that visibly shift over just a few decades. But there's more. Light from stars doesn't always take the same route. Earth moves, too. Its orbit around the Sun causes stars to seem to wobble. A tiny annual dance called parallax. This wobble is what lets us measure distance. And it's also what makes some stars seem to flicker in position, as well as brightness. So when a star twinkles, it's not always the atmosphere. Sometimes, the star is actually moving. Just slowly. Quietly. Like everything in the universe. Level 19, twin stars, twin lights. Some stars don't shine alone. In fact, most of the stars you see are part of binary systems. Two stars orbiting each other, locked in a gravitational dance. And sometimes, from Earth, they line up just right. One star passes in front of the other, partially blocking the light, then moving away. then passing again. This creates a rhythm, a steady pulse in the brightness, a flicker that repeats itself, like the heartbeat of a system in love. These are called eclipsing binaries. But there are others, too. Visual binaries, where you can actually see both stars twinkling next to each other. And spectroscopic binaries, where the twinship is hidden, revealed only through slight wobbles in their light. A single point of twinkling light might be two stars, or more, caught in a cosmic duet. And what you think is just a flicker might be a conversation between stars. Level 20, turbulence in the sky. Look up on a hot summer day, and you'll see the air shimmer above the pavement. Waves of heat dancing. The same thing happens in the upper layers of the atmosphere. Except there, the turbulence is invisible. It's made of shifting temperatures, winds, air pockets. This ever-changing sky bends and distorts the starlight, moment by moment. And astronomers? They fight back with something called adaptive optics. A telescope watches a star twinkle, then quickly adjusts a mirror hundreds of times per second to cancel the effect, like noise-canceling headphones. But for light. And sometimes we create our own fake stars. A powerful laser is shot into the sky, creating a glowing point in the upper atmosphere. By watching this laser star flicker, telescopes can map the turbulence in real time and sharpen the view. So behind every stable image of a star, there's a dance of machines, mirrors, and algorithms trying to quiet the sky. And every flicker you see with your eyes is the sky itself, alive, restless, moving between you. Level 23, twinkle on other worlds. What would starlight look like if you stood on another planet? On Mars, the atmosphere is thinner, just 1% the thickness of Earth's. But it's filled with fine dust that turns the sky a pale, dusty orange. Stars there don't twinkle much. They glow more steadily, but slightly dimmer, filtered through haze, instead of air currents. On Venus, the atmosphere is so thick, so full of sulfuric acid clouds, that no stars are visible from the surface at all. The sky is a dense, endless shroud. And the stars? They're hidden, silent. On Titan, Saturn's largest moon, you'd stand under a golden sky with methane clouds. The atmosphere is dense enough that it might scatter starlight just a bit, but only the brightest stars might manage to twinkle at all. And on the moon, no air, no atmosphere, no distortion. Look up from its grey, silent surface, and stars stare back, cold and still. Not a single flicker. So twinkling isn't something stars do. It's something that happens between them and us. A dance choreographed by air, by movement, by breath. The stars themselves are always steady. We are the ones who shimmer. Level 24, ancient eyes, ancient skies. Long before telescopes, before theories, before we knew what stars really were, people looked up and wondered. To the Babylonians, twinkling stars were the breath of the gods. signs that heaven was watching. To the Mori, the flickering of stars like Matariki was used to predict harvests and weather. To the Greeks, twinkling was part of a star's character. Fixed stars stayed put, while wandering stars, the planets, moved slowly, but didn't shimmer. They noticed the difference. Even without science, they knew. Planets don't twinkle. Stars do. And to the Navajo, twinkling stars were stories. Each movement, each glimmer, a part of a myth, a spirit. Twinkling wasn't just light. It was meaning. A message. A moment. Our ancestors didn't need modern tools to feel the wonder. They looked up, and the sky responded. Maybe it still does. Level 25, Why planets don't twinkle. You've heard it said before. Stars twinkle, planets don't. But why? The answer is in the light and the distance. Stars are so far away that each one is a single point of light. By the time it reaches your eyes, when the atmosphere bends it, there's no backup. The dot shifts, dims, wobbles. That's twinkling. But planets? They're closer. They don't appear as points, but as tiny disks of light. When air moves, parts of the disk get distorted, but other parts stay steady. It all averages out. So instead of flickering like a nervous candle, planets glow. Calm, firm, steady. You can use this trick next time you're not sure if a light in the sky is a star or a planet. Watch it. If it sparkles, it's a star. If it just glows, it might be Mars, or Jupiter, or Venus, the morning star. That isn't a star at all. Level 26, How our sun would look from afar. We see the sun every day as a blazing, blinding disk. But what if we could step away? If we traveled far enough to Pluto, to the outer edge of the solar system, the sun would shrink to the size of a coin held at arm's length. Keep going. Keep drifting. Leave the solar system. Hundreds of times farther. Thousands. And eventually, the sun becomes just like every other star. A dot. A single point of light. From Alpha Centauri, the closest star system to us, our sun looks like a modest star. In the constellation Cassiopeia, it twinkles too. Not because it changed, but because of the air between the viewer and the sky. It's strange to think. Our life-giving star, our warmth and light, our days and seasons, reduced to a pinprick from far away. But that's how we see all stars. And to someone else, somewhere out there, we are the star that twinkles. Level 27, How starlight carries information. Look closely. The light from a star isn't just light. It's a message. Every twinkle, every beam, carries more than just brightness. It carries the identity of the star. Split that starlight through a prism or a telescope's special sensor, and it spills out into a spectrum. A rainbow, but with dark lines scattered across it. These are absorption lines, unique to each element. They tell you what the star is made of. Hydrogen, helium, carbon, maybe iron, maybe lithium, maybe something stranger. They also tell you how fast the star is moving, toward you or away, by a tiny shift in color. Blue shift if it's coming, red shift if it's going, and even from light years away. We can measure a star's temperature, its size, its age, its spin, its fate. From one flickering point in the sky, we extract entire biographies. Light is a traveler. And the stars, they write letters. With every beam. Level 28, what twinkling reveals about alien worlds. Sometimes, a star doesn't just twinkle. It dims. Just a little. And it stays dim. For a few hours. Then brightens again. What happened? An exoplanet passed in front of it. We call this a transit. A faraway planet, blocking a sliver of starlight. As it moves across our view, with sensitive telescopes, we can measure the dip in brightness, even if it's just 1%, or less. And if that dimming happens again, and again, at regular intervals, we know something is orbiting there. Twinkling becomes data. Data becomes discovery. We now know thousands of planets outside our solar system. Many found this way by watching stars very, very carefully. Some are rocky. Some are gaseous. Some might hold liquid water. And all of them were hidden. Until one star flickered. In just the right way. Level 29, the rhythm of a star's flicker. When we talk about twinkling, we usually imagine a random sparkle. Irregular, chaotic, unpredictable. But some stars flicker with rhythm. These are called variable stars. Stars whose brightness naturally changes over time. Some brighten and dim in hours, some in days, some in months. There's one called Delta Cephei. Every 5.4 days, it pulses. Bright, dim, bright again. Like a heartbeat. Across hundreds of light years. And there's RR Lyrae. A whole class of stars that blink with metronomic regularity. Why? Inside these stars, layers of gas expand and contract. They breathe, in a way. They grow, shrink, grow again. And the light pulses with the motion. By studying the flicker, astronomers can measure the star's distance. Because the period of the flicker is tied to the true brightness of the star. Compare it to how bright it looks to us, and you can calculate how far away it really is. So that tiny pulse, that gentle shimmer in the dark, helps us map the scale of the entire galaxy. Level 30, when twinkling disappears. Have you ever seen an image from the Hubble Space Telescope? Those sharp points of light, the endless clarity, the almost overwhelming stillness. There's no twinkle. That's because Hubble and other space telescopes are above the atmosphere, with no air to disturb the light. The stars appear as they truly are, pinpoints of pure intensity. On Earth, even the most powerful telescope must fight the air. But in orbit, the view is clean, silent, almost haunting. This is why Hubble could capture the deep field, an image of a seemingly empty patch of sky. that, when stared at long enough, revealed thousands of galaxies. Not stars. Galaxies. Each with billions of stars of their own. Twinkling is beautiful. But sometimes we have to rise above it to see the full truth. Level 31, twinkling through a telescope. You might think, if stars twinkle to the naked eye, then through a telescope, they must look even more alive, even more dazzling. But the truth? Twinkling gets worse. Through a telescope. Because a telescope magnifies not just the star, but also the distortions in the air. Every layer of the atmosphere bends light in tiny, shifting ways. To our unaided eyes, it's a gentle sparkle. But zoom in, and you'll see stars dancing, wavering, pulsing, sometimes even splitting into strange shapes that shimmer and vanish. It's beautiful, but frustrating for astronomers who need precision. That's why observatories choose their homes carefully. High mountains, dry air, stable skies. It's not just for the view. It's to reduce the twinkle, to calm the sky. Still, even the best sights on Earth can't eliminate it completely. And so, science got clever. Level 32, adaptive optics, fighting the shimmer. Twinkling used to be a limit, a barrier, a stubborn flicker that blurred the edge of every image. Then came adaptive optics. Here's how it works. A laser is fired into the sky, creating a bright artificial star high in the atmosphere. Telescopes watch that star carefully, tracking how it twinkles, how the atmosphere is shifting light at that exact moment. And then, a mirror inside the telescope changes shape hundreds of times per second to cancel out the distortion, like noise-cancelling headphones. But for vision, the result? A ground-based telescope can see nearly as clearly as a space telescope. Twinkling, once a poetic limit, becomes a solvable problem. It doesn't make the stars less beautiful, just a little easier to understand. Level 33, when the stars vanish, light pollution. Once, the night sky was a vast ocean of stars. But now, in many cities, you look up and see nothing. Maybe the moon, a planet or two, and if you're lucky, a handful of the brightest stars. The rest? Drowned. Light pollution is the quiet erasure of the cosmos. Street lamps, neon signs, billboards, floodlights, windows that never go dark. They all push light upward, where it scatters in the atmosphere and hides the stars behind a haze. The sky glows, not from the heavens, but from us. In heavily lit cities, you might see only 20 or 30 stars. But out in the wilderness, with no artificial light, you might see thousands. Even the cloudy river of the Milky Way. Twinkling is a gift we're slowly covering over. And it's not just stargazers who lose. Light pollution affects birds, insects, turtles, ecosystems. Even our sleep, circadian rhythms, are thrown off by a night that never arrives. Twinkling isn't just beauty, it's balance. And restoring the stars might just restore a bit of us, too. Level 34, twinkling in myth, poetry, and song. Long before we knew about atmospheric refraction, long before prisms and spectrometers, humans noticed the stars twinkle, and they gave it meaning. The ancient Greeks saw stars as divine fires, flickering with the moods of the gods. The Chinese, in their old star charts, watched for changes in brightness as signs of luck or warning. In Hindu texts, the stars shimmered as celestial messengers, watchers of fate. And in poetry, we all know it. Twinkle, twinkle, little star, the lullaby of lullabies, an 1806 poem by Jane Taylor, later set to music, passed through generations, translated into dozens of languages. That sparkle in the sky, it always stirred something. A longing, a question, a tiny flicker of connection. Science can tell us how stars twinkle, but poetry tells us why we care. And maybe we need both. Level 35, does the moon twinkle? You've seen it. A perfect silver disk. Steady. Bright. Still. The moon doesn't twinkle. But why not? After all, the moon is up there, bathed in the same atmosphere as the stars, seen through the same layers of shifting air. The difference? Size. Stars are so far away that their light reaches us as a single point. And when that one point passes through turbulent air, it jumps, bends, flickers, because there's no other light to balance it out. But the moon? It's close. It spans half a degree of the sky, wide enough that even when some parts are distorted, the whole thing stays steady. It's like watching a distant candle through a heat wave. It flickers. But a bonfire? You still see it clearly, even through the same hot air. The moon's light does waver slightly if you look closely through a telescope. But to your eye, it remains calm. A soft, silver anchor in a sea of flickering stars. Sparkles level 36, do stars twinkle on other planets? Imagine this. You're standing on Mars. The sky is a dusty red-gray, and night is falling. Would you look up and see stars twinkling, just like on Earth? The answer is kind of. Twinkling depends on an atmosphere, and Mars does have one. But it's very thin, just 1% the density of Earth's. That means less atmospheric turbulence, less shifting of light, less twinkle. Stars seen from Mars would mostly look sharp, almost like from space, but with a faint, subtle shimmer. Now try Venus. Its atmosphere is thick, dense with carbon dioxide, and constantly churning with stormy winds. If you could survive long enough to look up, you'd probably see stars wobble and flicker dramatically, maybe even disappear behind thick clouds. And on the moon? With no atmosphere at all, the stars shine with perfect clarity. No twinkle, no shimmer, just still, silent light. So twinkling isn't a universal truth. It's not about the stars. It's about where you're standing when you look at them. Level 37, how astronomers erase the twinkle. For centuries, twinkling was just accepted. A poetic nuisance. A blur you couldn't control. But in the modern age of astronomy, precision matters. Tiny shifts in light can reveal a planet orbiting a distant star, or the wobble of a galaxy's edge. So how do we get rid of twinkle? We already met adaptive optics back in level 32. Those brilliant mirrors that shapeshift to cancel atmospheric distortion. But there's more. Some telescopes use interferometry, a method where light from two or more telescopes is combined digitally, creating a virtual telescope as big as the space between them. This technique can cancel out distortions and resolve incredibly fine details. Others go even further, launching telescopes into space, like Hubble or James Webb, where the stars don't twinkle at all. They just burn. Pure, steady light, reaching us after millions of years, finally uninterrupted. So while we may love the twinkle, science sometimes needs clarity. And slowly, bit by bit, we're learning to tame the shimmer. Level 38, when stars explode, twinkle turns to blaze. What's the opposite of a gentle flicker? A supernova. A dying star's final act. Sudden, violent, and unimaginably bright. For a moment, a single star can outshine an entire galaxy. No longer a twinkle, not even a pulse, but a detonation of light. Some supernovae are so bright they can be seen in broad daylight from Earth. In 1054 CE, Chinese astronomers recorded a guest star that shone in the sky for weeks. It was the Crab Nebula being born. And unlike twinkling, which comes from the atmosphere, a supernova's brilliance is real, authentic, coming from deep within the star itself. It's light that carries the end of something, but also the beginning, because the elements forged in a supernova, carbon, oxygen, iron, are scattered across space. They become planets. They become oceans. They become us. So that blaze? It's not just death. It's the echo of Level 39, Twinkling and Time, how far the light has traveled. When you look at a star, you're not seeing it as it is now. You're seeing it as it was years ago. Centuries. Sometimes millennia. Because light doesn't arrive instantly. It moves fast. But space is vast. The nearest star system, Alpha Centauri? Its light takes over 4 years to reach us. Some of the stars twinkling above you tonight might have died long ago. Their light is just now completing the journey to your eyes. So that shimmer in the sky? It's not only atmospheric. It's temporal. You're watching light that began moving before you were born. And not just light, but stories. Because every twinkle is a kind of message. A photon whisper from the past. Some stars shine from the time before there were humans. Before Earth had trees. Before the moon even existed. Twinkling reminds us, what we see is never the whole truth. Only the part that's reached us so far. Level 40, binary stars, how their dance affects the shimmer. Most people imagine stars as lonely. A single light, burning alone in the black. But the truth? Over half of all stars are in binary or multiple systems. They orbit each other. Sometimes close. Sometimes far. Locked in a celestial dance. And this affects their light. As they orbit, they eclipse one another, or shift brightness, or stretch each other into egg shapes. that flicker slightly with every spin. To the naked eye, they might still look like a single point, but their brightness subtly changes with rhythm. That's not twinkling from air. That's twinkling from motion. And some of these stars, like the famous Algol, were seen flickering by ancient sky watchers who didn't understand orbits, but noticed the pattern. In a way, those variable lights were the universe's first code. Before we had telescopes, before we had language, the stars were already pulsing with meaning. Level 41, when starlight bends, gravitational lensing. You've heard it by now. Twinkling comes from turbulence in the air. But there's another kind of distortion. A deeper one. One that bends space itself. It's called gravitational lensing. When light passes near a massive object, like a galaxy cluster or a black hole, gravity pulls on the space around it, and the light follows the curve. It's like watching the stars through a glass of water. But this glass is made of gravity. Sometimes a single star appears as two, or even a ring of light, called an Einstein ring, surrounding the object in the middle. It's not twinkling, but it's a kind of shimmer, a cosmic illusion. Gravitational lensing has let us see galaxies that would otherwise be invisible. Light bent around corners from the farthest reaches of the universe. It also lets us detect dark matter by measuring how it warps light, even though we can't see it directly. So while the twinkle comes from Earth's air, there's another kind, from the fabric of space itself. Not a flicker, but a lens into the unseen. Level 42, the edge of visibility, magnitude and brightness. Not all stars twinkle equally. Some burn like beacons. Others barely whisper. This is where magnitude comes in. A scale astronomers use to measure how bright a star appears. The lower the number, the brighter the star. Sirius, the brightest in our sky, has a magnitude of -1.46. The faintest stars you can see with the naked eye? Around +6. But here's the trick. Magnitude doesn't mean actual brightness. A tiny star nearby might look bright. A massive one far away might barely glow. The twinkle you see is shaped not just by air, but by this apparent magnitude. Fainter stars shimmer more erratically, their fragile light more easily disturbed. Brighter stars? Their brilliance holds steadier through the distortion. And with a telescope, you can peer far beyond +6 to +15, +20, even fainter. In the blackness, you'll find stars so dim you'd never know they existed without help. And yet, there they are, twinkling softly at the very edge of seeing. Level 43, twinkling under ancient skies. Long before satellites, before telescopes, before even the compass, there were only the stars, and they twinkled just the same. But for our ancestors, that flickering wasn't just a quirk of light. It was communication. Many early cultures believed that the stars were alive, watching, pulsing, sending signs from above. In ancient Polynesia, navigators read the shimmer of starlight to guide canoes across the Pacific, tracking the brightness, position, and twinkle. to know when a star was near the horizon or hidden by stormy weather. The ancient Greeks noticed how some stars flickered more than others and classified them accordingly. They believed excessive twinkling meant a star was watery or unstable. In China, during the Han Dynasty, royal astronomers recorded the flicker of certain stars as omens, warnings of political shifts, natural disasters, or divine messages. And even now, in many indigenous communities, twinkling stars are more than science. They're signals of seasons, of ancestors, of change. Before science gave us adaptive optics and spectrographs, people looked up and saw truth in the way a star danced. They didn't need numbers to believe the sky was alive. Level 45, the chemistry of starlight, what the twinkle tells us. It might seem like twinkling is just a shimmer, an optical accident. But with the right tools, that shimmer becomes a language. Light carries information, not just brightness or position, but composition. When starlight passes through a prism or a diffraction grating, it spreads out into a spectrum, a rainbow made of data. This spectrum isn't smooth. It's filled with tiny gaps, called absorption lines. Each element, hydrogen, helium, carbon, oxygen, absorbs light at very specific wavelengths. And so each leaves its fingerprint in the spectrum. By reading those patterns, astronomers can tell what a star is made of, how hot it burns, how fast it spins, how far it's traveling, whether it has planets, even what kind of star it is. A newborn, a giant, a dying white dwarf. So when you see a star twinkle, you're watching light that has traveled across space, carrying coded messages about the heart of a sun you will never touch. And all that from a shimmer in the sky. Level 46, when stars vanish, clouds, light pollution, and silence. Not every night is a canvas of stars. Sometimes you look up and find only black clouds, thick and slow, rolling across the sky, like heavy thoughts you can't shake. Or maybe you're in a city, surrounded by neon signs, LED streetlights, and glowing skyscrapers. The stars are still there, but the light around you drowns them out. This is called light pollution. And it's more than just a nuisance. It affects wildlife, sleep cycles, and even our mental health. Because the sky is supposed to be vast, not empty. It's strange how much we miss what we barely noticed before. And yet, if you've ever driven into the countryside or camped far from the city, you'll remember the moment the stars came back. Maybe you even gasped, because the night sky, truly dark, is overwhelming. So the next time it's cloudy, or the sky feels empty, know that the stars haven't gone. They're still up there, still twinkling, still waiting for the world to go quiet again. Level 47, how star twinkling inspired art, poetry, and lullabies. Not everything about twinkling needs to be measured. Sometimes it's enough just to feel it. For centuries, the flicker of starlight has moved poets and painters more than scientists. Van Gogh saw the night sky not as static, but alive. His brush strokes stars spinning, swirling, flickering like they were breathing. In Twinkle, Twinkle, Little Star, a nursery rhyme sung in dozens of languages, the twinkle becomes a question, not of science, but of wonder. How I wonder what you are, even if we knew completely what they are. The shimmer remains beautiful. The Persian poet Rumi wrote, "You were born with wings, why prefer to crawl through life?" A line often imagined under a night sky, where stars twinkle like thoughts just out of reach. The Japanese haiku masters often used stars as symbols of change, transience, a flicker of life before the dark. And in lullabies, the twinkle tells us something gentle, that even in darkness, there is light. Maybe we love twinkling stars because they remind us that even the universe has a heartbeat. Level 48, the science of seeing, your eyes versus the telescope. The human eye is amazing, but it's also limited. When you look at a star, you're seeing photons. That took years, sometimes thousands of years, to reach you. But those photons must pass through your cornea, lens, and retina, all shaped by biology, not precision. Your brain stitches the image together, flipping it right side up, filling in gaps. It guesses, and sometimes it guesses wrong. That's part of why stars twinkle. But a telescope? That's a different set of eyes entirely. Telescopes use mirrors, sensors, and algorithms. No fatigue, no tears, no blinking. They can see light far beyond the visible spectrum. Infrared, ultraviolet, X-rays. A star that seems ordinary to you might be erupting, spinning wildly, or shedding matter into space. But your eye can't tell. With a telescope, especially in space, there's no atmosphere to distort the image. No shimmer. Just light. Clean, sharp, and full of secrets. And yet, even with all that data, there's something special about seeing a star with your own imperfect eyes. The twinkle reminds you, you are here. You are watching. You are part of it, too. Level 49, the invisible stars, X-rays, gamma rays, and radio light. Not all stars twinkle. At least, not in a way we can see. Your eyes are tuned to a narrow band of light, the visible spectrum. But stars don't just emit visible light. They blaze across the entire electromagnetic spectrum, from low-energy radio waves to searing gamma rays. And depending on what part of a star's life it's in, or what it's doing, you might need different eyes to see it. Radio telescopes, like the giant dishes in Chile or Puerto Rico, let us hear stars, or at least detect their lowest frequency emissions. Some stars pulse in radio waves. They're called pulsars, the collapsed cores of supernovae, spinning rapidly and beaming radio waves like a lighthouse. Then there are X-ray telescopes, like NASA's Chandra Observatory, which reveal violent, high-energy stars. Systems where one star is stealing matter from another, or where black holes are eating starlight. Gamma-ray detectors pick up on the most extreme events. Exploding stars, neutron star collisions, and the birth of black holes. None of these twinkle like a star in your backyard sky. But they shine. And each frequency of light tells a different story. Your eyes see the poetry. The instruments see the physics. Together, they give us the whole sky. Level 50, when stars pretend to twinkle, satellites, planes, and tricks of the eye. Sometimes you look up and see something twinkling brightly, quickly, oddly. It flashes, moves slightly, then vanishes. But it wasn't a star. It might have been a satellite. Low-orbit satellites often reflect sunlight just after sunset or before sunrise. They can appear as fast-moving, twinkling dots crossing the sky. Iridium flares, now largely retired, were once known for their brilliant, sudden flashes caused by sunlight reflecting off their antennas. Then there are planes. Their blinking red and white lights can look like twinkling stars at first, until they move or hum softly overhead. And sometimes the twinkle is from you. Your eyes might be tired or dry. Your focus might shift slightly, and a bright object can seem to shimmer, even when the atmosphere is still. In winter, when the air is cold and dry, twinkling is sharper, more defined. In summer, warm and hazy nights soften the shimmer. So sometimes the twinkle is real. Sometimes it's a machine. Sometimes it's just you. The sky isn't lying. But it does enjoy a little mystery. Level 51, Twinkling Stars in Science Fiction and Space Stories. Long before we had telescopes, or data, or spectrometers, we had stories. Twinkling stars were signals, messages, warnings, hopes. In science fiction, stars often act as symbols of distance, longing, or something just out of reach. In Arthur C. Clarke's Childhood's End, the stars represent both beauty and loss, a sky that humanity is slowly outgrowing. In Star Trek, the stars are a destination, each flicker a promise of new life, new civilizations. In Ray Bradbury's The Martian Chronicles, twinkling stars are seen by lonely humans, stranded on a red desert world, looking back toward Earth and remembering what they left behind. Even in children's stories, the stars twinkle as guides. Think of the second star to the right. In Peter Pan, leading to Neverland. In Studio Ghibli films, like Howl's Moving Castle, stars often shimmer not just in the sky, but inside characters' hearts, as literal fire, as fate, as wonder. So twinkling isn't just a physical effect. It's a literary one, a narrative tool. One that says, something is out there. And maybe something is inside you, too. Level 52, do stars twinkle on other planets? It's easy to forget how Earth-centered our view is. Twinkling happens because of our atmosphere. Turbulent layers of air bending the light before it reaches our eyes. But what about other planets? On the Moon, there is no atmosphere. If you stood there and looked up, the stars would not twinkle. They'd shine steadily, sharply, in the black sky, even during the lunar day. On Mars, Things get interesting. Mars has a thin atmosphere. Just 1% the pressure of Earth's. And it's full of dust. During a dust storm, sunlight diffuses wildly. But stars at night? They would twinkle. Just a little. Perhaps softer. Slower. And redder. On Venus, the atmosphere is so thick and full of carbon dioxide and sulfuric acid that starlight would be almost entirely blocked. Even if you could see stars from the surface, the dense atmosphere might make them blur, shift, and vanish long before you could say they were twinkling. On Jupiter, with its deep gas layers and massive storms, a hypothetical floating observer might see something more dramatic. Starlight bending wildly in a ballet of chaos and heat. So the short answer? Yes. Stars can twinkle on other planets. But the twinkle changes. Like a fingerprint. Unique to every world. Just like us. Level 53, Ancient Cultures and Their Stories of the Twinkling Stars. Before satellites. Before telescopes. Before clocks and calendars. There were stars. And they twinkled. Across the earth. Cultures noticed this flicker. And built meaning from it. To the Greeks, the shimmer of stars was divine. The glittering bodies of gods, watching from the celestial sphere. In Aboriginal Australian tradition, twinkling stars were messages from the ancestors. The sky was not distant. It was present. Alive. Each sparkle. A voice. The Inca read the dark spaces between stars. And when stars flickered oddly, they believed it was the gods, warning of weather, of drought, or political unrest. In ancient China, star twinkling was part of celestial omens. A star that changed in brightness, or flickered too much, might indicate a coming storm, an emperor's death, or a new dynasty. Navajo stories tell of stars as sparks from a sacred fire, tossed into the sky by the holy people. They twinkled because they still burned. The Polynesians, master navigators, watched the flicker of stars on the ocean horizon to guide their canoes across thousands of miles of sea. And to many, the twinkling stars were simply loved ones, watching from above. A belief that needs no telescope. So long before we measured light curves or atmospheric distortion, we understood something deeper. Twinkling meant connection between earth and sky, between past and present. Level 54, what a photon really is, and how it carries starlight to us. Now we return to science. But don't worry. This isn't the sharp, cold kind. This is soft science. Slow. Sleepless. So, what is light, really? A photon is the smallest unit of light. It's not a particle like a marble. Not a wave like water. It's both. And neither. A photon is a packet of energy. A shimmering thing. With no mass. No rest. It always moves. At the speed of light. Because it has no choice. A photon from a star might have been created in the heart of a fusion reaction, where hydrogen became helium and released energy that photon might spend thousands of years bouncing around the inside of the star, trying to escape, like a moth trapped in a hall of mirrors. And then, finally, it leaves. It travels across light years of vacuum. Maybe it passes a rogue planet. Maybe it's bent slightly by gravity. But it never stops. Until, one night, it hits your eye. Just one photon. From a star that might not even exist anymore. And your brain turns it into a twinkle. In that moment, you've connected with something ancient, distant, and fleeting. And maybe that's enough. Level 55. Why blue stars twinkle differently than red ones. Not all stars twinkle the same way. Some flicker quickly. Sharp, icy flashes. Others shimmer slowly. A gentle pulse. This difference comes down to color. And color, in astronomy, means temperature. Blue stars are hotter. They burn at temperatures above 10,000 Kelvin. They emit shorter wavelengths of light, which scatter more easily when passing through Earth's atmosphere. Like sunlight on a hazy afternoon. The shorter the wavelength, the more it gets disturbed. So blue stars, especially when low in the sky, twinkle more. Their light dances harder, fractures quicker. Red stars, like Betelgeuse, are cooler, burning at around 3000 Kelvin. They emit longer wavelengths, which pass through the atmosphere more smoothly. So red stars appear steadier, slower to flicker, like a dying ember in the sky. But even more, sometimes you can see color twinkling when the atmosphere is especially turbulent. A single bright star can seem to flash red, blue, green, and white in rapid succession. This is more common near the horizon, where your line of sight cuts through more atmosphere, more layers, more chaos. You can try this. Go outside on a clear night. Look toward the horizon and find a bright star low in the sky. Watch it long enough, and you might see it flicker like a jewel, a kaleidoscope of starfire. The twinkle, then, is not just light. It's color in motion. Level 56. How astronomers correct twinkle using adaptive optics. Twinkling is beautiful. But to astronomers, it's a problem. When you want to study a star's surface, or see exoplanets, you need the light to be stable, undistorted, uncorrupted. And that's where adaptive optics comes in. Adaptive optics is a technology that cancels out the atmosphere's effects in real time. Here's how it works. A laser is fired into the sky, creating an artificial guide star, a bright point the system can watch. As the atmosphere distorts the guide star, a computer instantly measures the changes. Then, a deformable mirror, a flexible surface that can change shape thousands of times per second, bends to cancel out the distortion. It's like a wave cancelling a wave. The result? A much sharper image. Stars that should twinkle don't. They hold still. Thanks to adaptive optics, ground-based telescopes can now rival the clarity of space telescopes, like Hubble, and in some cases, surpass them. From Earth, we can now see the rings of exoplanets, The surface of distant stars. The gas spirals around a black hole. All because we learn to hold the sky steady. For all its beauty, sometimes we want the stars to sit still, just long enough to truly see them. Level 57, twinkling through water, why stars shimmer when seen from under the sea. Imagine you're beneath the ocean, goggles on, floating just below the surface. You look up. Above you, light. But not still. Not solid. It dances, shimmers, fractures into 1,000 gleaming shards. And if it's night, and if the moon is bright, or the stars bold enough, they twinkle too. Not because of air, but because of water. This is refraction, a bending of light as it moves from one medium to another, just like air in the atmosphere. Bend starlight to make it twinkle. The rippling surface of water bends light in a more dramatic way. Every tiny wave, every ripple, every breath of current creates a constantly shifting lens. So a star viewed from under the water doesn't just twinkle. It explodes into streaks and splinters of light, like fireworks slowed down. And if you've ever opened your eyes in a swimming pool at night, you've seen this. Stars turned liquid, constellations scattered. This effect even inspired early seafaring myths, stories of gods and spirits who lived not in the heavens, but beneath the ocean's mirror. Because under the sea, the sky doesn't shine. It swims. Level 58, how stars look from the poles, equator, and different latitudes. Now let's return to solid ground. But not just one kind of ground. Let's move across the Earth. From pole to pole. Equator to edge. Because where you are changes everything about the stars you see. At the equator, the night sky spins overhead like a wheel. You can see both hemispheres. The northern constellations, like Ursa Major and Cassiopeia, and southern ones, like Crux, the Southern Cross. Stars rise straight up and set straight down. They twinkle more at the horizon, less overhead. But if you move toward the poles, things slow down. In the Arctic or Antarctica, the stars seem to circle you. Some never rise. Some never set. This is because of your angle. You're standing nearly sideways to the equator's rotation. And then there's the North Star, Paul Aries. From the North Pole, it sits almost directly overhead, a steady beacon. And near it, stars spin in perfect circles, never dipping below the horizon. In contrast, at the equator, Paul Aries is almost invisible. It hugs the horizon, barely rising. And this changes twinkling too. Closer to the horizon, you look through more atmosphere. So stars shimmer harder. That's why people living in tropical or equatorial areas often see brighter, more active twinkles than those in polar regions. And in the poles, where the stars glide sideways, you may see a kind of slow, eerie drift. A stillness that feels ancient. So even on Earth, twinkling isn't fixed. It depends on where you are, how you look, and how long you stay awake. Level 59. Why stars don't twinkle during the day. Look up, right now. If it's daytime where you are. Can you see the stars? No? But they're still there. All of them. Millions above your head. Just as bright. Just as distant. So why don't they twinkle? Because they've been outshined. The sun, our closest star, floods the atmosphere with light, and light, like fog, spreads. The blue sky you see is sunlight scattered by air molecules. This scattering, called Rayleigh scattering, is the same reason why stars twinkle at night. But during the day, the atmosphere is already so flooded with scattered sunlight that the faint light of distant stars gets lost. And even if you could block the sun, say, by hiding behind a building or going underground, the scattered daylight would still mask most stars. So it's not that they stop twinkling. It's that we can't see their flicker through the sunlight's roar. In rare conditions, like during a total solar eclipse, the sky darkens enough to reveal a few bright stars. And for a few minutes, in that strange twilight, you may glimpse them again, twinkling, even though the sun hasn't set. Level 60. Do planets twinkle too? Have you ever noticed some bright stars in the night sky don't seem to twinkle? They shine steadily, calmly, almost suspiciously still. Those are likely planets. Planets, unlike stars, don't twinkle as much, especially when they're high above the horizon. But why? The difference is in distance. Stars are incredibly far away, so far that they appear as single points of light. This means any small distortion in the atmosphere makes their light bend, scatter, and flicker. But planets are closer, much closer. And while they still appear small to the naked eye, they're large enough that their light arrives at Earth from a slightly broader area. This makes the atmospheric distortions average out a little more, so the light we receive is steadier. Not always, though. If a planet is low in the sky, or the atmosphere is especially turbulent, even planets can appear to twinkle. Venus, the evening star, can shimmer like a diamond when it's close to the horizon. Mars sometimes flashes red, not because it's changing, but because of us. But in general, if you're looking for a steady, bright object in the early night sky, and it doesn't twinkle, you might be seeing a fellow traveler. Not a burning sun, but a wandering world. Level 61. How stars twinkle on other planets, Mars, Venus, and Titan. You're standing on Mars. The sky is butterscotch orange, thin and dusty. No birds. No clouds. Only quiet wind. An ancient stone. Night comes. And the stars? They twinkle, but not like on Earth. Mars has a much thinner atmosphere. Only about 1% the density of Earth's. So while there is air, it's sparse, dusty, dry. This means there's less distortion. But when dust storms roll in, and they often do, they fill the sky with particles that can cause shimmering. Not from air movement, but from dust scattering. So twinkling on Mars is rarer, but sometimes more intense. When dust is thick and the wind fast. Now travel to Venus. You can't stand on the surface. Not really. It's a furnace. But imagine you could. You'd see no stars. Venus's atmosphere is thick, 90 times denser than Earth's, and filled with clouds of sulfuric acid. Light barely gets through. The surface is dim, like twilight all day long. And stars? You'd never see them from the ground. But in orbit, above the clouds, you'd see stars. Sharply and without twinkle. Just like in space. And now, let's go farther. To Titan, Saturn's largest moon. A world of methane lakes, ice rocks, and an orange haze. Titan has a thick atmosphere too. But it's nitrogen and methane. With strange weather. And gentle winds. A stargazer on Titan might see stars dimmed and hazy, sometimes flickering, through its smog-like sky. The twinkle there wouldn't be like ours. Not sharp or crisp, but muffled, like light trying to reach you through fogged glass. So in each world, the stars still shine. But how they reach your eyes depends entirely on the veil they pass through. Level 63, How Stars Helped Ancient Travelers Navigate. Before GPS. Before compasses. Before written maps. We had the stars. Not just to admire, but to follow. To survive. Across deserts, oceans, and endless plains. People learn to read the sky. Like a familiar book. In the Northern Hemisphere, there was one guide above all. Polaris. The North Star. Unmoving. Constant. A quiet anchor in the sky. Because Polaris sits almost directly above the North Pole. It shows you north, always. Sailors would measure how high Polaris was above the horizon to estimate latitude, how far north or south they were. In the Southern Hemisphere, where there's no bright pole star, navigators used the Southern Cross and its axis to point toward the South Pole. But stars didn't just show direction. They told time. As the Earth turns, constellations rise and set in predictable ways. On long voyages, Polynesian wayfinders memorized entire star paths, sequences of stars that guided them from island to island. No compasses, no charts, only memory. Waves, birds, clouds, and stars. They trained for years and passed it on. Not with books, but through stories and songs. So the sky wasn't just for dreaming. It was a map, a clock, a companion that never left. Even now, when you fly across continents, the plane still quietly calculates position. From the stars. Invisible to you, but always there. Level 64, What animals see when they look at the stars. And it's not just humans who look up. Some animals, too, seem to sense the stars. Let's begin with migrating birds. Each year, millions of birds fly thousands of kilometers, often at night. How do they stay on course? Studies with songbirds showed that many species use the stars for navigation. In experiments, birds in a planetarium oriented themselves correctly only when they could see a realistic star pattern. When the star map was reversed, so was their direction. Some species learn the rotation of the night sky as fledglings, using the apparent movement of stars to find north. It's not instinct alone. It's learned. They memorize the sky. But birds aren't the only ones. Dung beetles, in a surprising twist, also use the stars, even the Milky Way, to roll their tiny balls of food in straight lines across the desert. They climb atop their ball, look up, and set their course. Without stars, they wander. And then there are sea turtles, moths, even seals, whose nighttime behaviors show signs of celestial orientation. To us, the stars are beautiful. To them, their survival sparkles, and so the sky belongs to many, not just to poets, astronomers, and dreamers, but to turtles, and beetles, and birds with silent wings, cutting through starry winds. Level 65, the music of the stars, sonification and stellar vibrations. You may think stars are silent, and to our ears, they are. No air, no sound waves. Space is quiet. But stars vibrate. Their surfaces ripple, like water disturbed by wind. These oscillations, called stellar seismology, can be measured. Inside each star, pressure and gravity cause waves to bounce and resonate. And from these waves, scientists can translate light into sound, a process called sonification. They take the data, brightness variations, frequencies, oscillations too slow for human ears, and speed them up, shift the pitch, until we can hear the rhythm. The result? A star becomes a song. Some stars pulse gently, like a low heartbeat. Others shimmer like chimes. A red giant may boom with deep tones, while a white dwarf sings sharp and fast. Each star has its own acoustic fingerprint. And this isn't just art. It's science. By listening to these tones, astronomers can probe a star's interior, its age, its structure, its future. Even the sun has a voice. NASA recorded the sun's oscillations and converted them into deep, rumbling tones. A slow, mighty breath from the heart of our system. So next time you look at a star, know that it sings. You just need the right ears. Level 66, Stars in Mythology, the divine stories of twinkling light. Before science explained atmospheric turbulence, ancient people looked up and saw magic. Twinkling stars weren't just points of light. They were gods, spirits, souls, omens. In Greek mythology, many constellations are rooted in myth. Orion, the hunter, placed in the sky by Zeus. Andromeda, chained to the rocks, rescued by Perseus. Her story still painted in stars. The Pleiades, 7 sisters, fleeing a pursuer, turned into a glittering cluster in the sky. In Chinese mythology, there's the tale of Xinu and Niulang, a weaver girl and a cowherd, separated by the Milky Way, allowed to reunite only once a year, when magpies form a bridge. This story gave birth to the Qixi Festival, a romantic holiday celebrated in summer. In indigenous Australian lore, the stars were tools, calendars, and stories of the dreamtime. The emu in the sky, made not from stars, but from the dark gaps in the Milky Way, told stories of life, birth, and balance. And in Inuit traditions, the stars were often souls of ancestors, watching from above, offering guidance and presence. In the harsh Arctic night, so much of the world's mythology is etched into the sky. Before paper, before books, we wrote our deepest hopes in the stars. Sparkles and still we do, when we name stars after those we've lost, when we make wishes on a flicker, when we trace lines in the dark and make them stories. The sky is full of memories. Level 67, The Physics of Light, Why Starlight Bends and Stretches. You see a star, and you think, that light is coming straight to me. But in truth, it's taken a winding journey. Light moves fast, almost 300,000 kilometers per second. Yet space isn't empty, and light isn't immune to detours. When a star's light enters our atmosphere, it hits layers of air with different temperatures, densities, and movements. This causes refraction, bending the light just slightly. Each layer bends it a little differently, causing the star to appear like it's shifting, twinkling. But light can bend in space, too, when it passes near a massive object, like a galaxy or black hole. Its path curves. This is called gravitational lensing. Einstein predicted it, and we've seen it. Sometimes, a single star's light is bent so much that we see it twice, or 4 times, or in a ring, a perfect halo of illusion. Light can also stretch. As the universe expands, light traveling across it gets pulled apart. Its wavelength increases, becoming more red. This is redshift. When we see distant galaxies, their light is redder than it started. Not because they're actually red, but because they're rushing away from us. And space itself is stretching. Light is not just a beam. It's a storyteller. And every flicker from a star carries the tale of everything it passed through to get here. Level 68, What it means to see a star that already died. You've heard it before. The stars we see might already be dead. But what does that really mean? A star sends out light, traveling across unimaginable distances. Some are close. Proxima Centauri's light reaches us in just over 4 years. Others take longer. Hundreds, thousands, even millions of years. So when you see a star that's, say, 500 light-years away, you're seeing what it looked like 500 years ago. You're seeing its past. And in that time, it may have changed, grown older, collapsed, exploded into a supernova, or faded into a cold remnant. But you won't know. Not until that updated light reaches you. So yes, some of the light you see comes from stars that no longer exist. It's like watching a slideshow of the universe. But every photo is delayed. Some by a few years. Some by eons. And it's humbling. Because the sky you see above you isn't the present. It's a tapestry of time. A history book made of photons. And you, just by looking up, are reading it without even realizing. Sparkles so tonight. Look at the stars. But know this? They're not just shining. They're traveling, bending, stretching, and maybe already gone. Level 69, the cosmic dust that dims and colors starlight. Sometimes a star doesn't twinkle clearly. It seems dimmer, redder, as if there's a filter between you and it. And there is. Cosmic dust. Not the kind you brush off a table. This dust is ancient. Microscopic grains of carbon, silicon, and ice. Floating between stars. The leftovers of old supernovae. The building blocks of future planets. When starlight travels through these clouds, shorter wavelengths, like blue and violet, scatter more easily. What gets through is the redder light. This is called interstellar reddening. The star hasn't changed, but the light it sends is filtered by space itself. And the more dust it passes through, the more its light dims. Sometimes, entire stars can be nearly hidden, reduced to faint glows, or veiled shadows. Astronomers account for this. When measuring star brightness, they use infrared sensors to see through the dust, just like your eyes adjusting in a dark room. But here's something lovely. This dust, this obstruction, is also essential, because these clouds are where stars are born. Inside these cold, dark nurseries, gravity gathers gas and dust. Slowly, quietly, until a new star ignites. So yes, dust dims the light, but it also makes new light possible. Level 70, binary stars, when two stars dance in gravity's embrace. Not every star is alone. In fact, most stars in our galaxy are part of binary systems. Two stars, locked in orbit around each other. Sometimes they're close, circling each other like tightrope dancers. Sometimes they're distant, tugging gently, each aware of the other. Across millions of kilometers, they don't twinkle alone. They pull on each other, shape each other's paths, and in some cases, even swap material. In an eclipsing binary, the stars pass in front of each other, from our view, causing dips in light. As one hides the other. This is how we've discovered many invisible stars, like black holes, which have no light, but still pull on their glowing companions. And when two white dwarfs or neutron stars orbit each other, they may spiral inward and merge, causing explosions so powerful we detect them across the universe. And yet, sometimes the dance is gentle. A red dwarf and a sun-like star, spinning together for billions of years, never colliding, never separating, just coexisting, forever in motion. It's easy to imagine stars as distant, solitary things. But more often, they are in relationships, gravitational conversations, across time and space. Sparkles dust. Dancing stars. And the way light weaves through both. The sky is full of partners. Some near. Some never touching. But always connected. And just like that, we've reached the end of this quiet path together. From that first shimmer in the sky, to the science tucked inside each flicker, you've traveled across atmospheres, wavelengths, gravitational bends, and centuries of wonder. Maybe you didn't realize just how much light can whisper, how even the softest twinkle carries secrets of distance, motion, and time. If you made it all the way here, whether fully awake or gently drifting, thank you. This video might be ending, but the night still has room for more. So if you found a moment of peace, or learned something new, don't forget to like. Just a small way to let this light reach others too. Tell me in the comments how your night is going. Leave a timestamp for the moment that made your mind pause, or your heart slow down. And if you'd like to stay a little longer, subscribe. There are many more sleepless nights ahead, and stories waiting in the stars, in science, in silence. Until next time, this has been For Your Sleepless Night and the Sleepless Me. Crescent Moon. Rest gently.